So here's the ETC homepage. The URL is jwst.etc.stsci.edu. It's as short as that. And we have some information here that I'll go through really briefly. We have a news section, which includes the current version of the ETC. We are currently in version 3.0, which matches with the cycle 3 proposal period. We have some information on what makes this version, what's new in this version, links to release notes and known issues, and then information on how to take your old workbooks from previous versions and make them editable again. We also have a little help box here, which includes a link to the videos that I mentioned before, and also a link to the documentation, and then a README that includes some additional information about some of the under the hood workings and some caveats about spamming the system when things start getting slow. Up here in the top right, we have a help menu, which includes the user guide, which is the documentation, links to known issues and release notes in the knowledge base, and then a direct link to the help desk. And this About button includes the archive link to the Pontoppidan 2016 paper I mentioned earlier. Okay, so there are a few buttons here at the top. From left to right, we have Quick Start. This is a quick way to walk through DTC and figure out which buttons you have to push to get a calculation for a point source to complete. And that's what I'll walk through a little. I won't walk through the quick start itself, but I'll walk through the process of doing point source observations for a decent portion of this JWebbinar. The second button here is to create a new user. This is how you create a MyST account. The importance of having a MyST account is that it allows you to log in. So the login option allows you to save workbooks and share workbooks with other users. If instead you choose to work anonymously, you will not be able to save your workbooks, and you will not be able to share your workbooks with anyone. And there will be a 10 workbook limit for anonymous users. It's recommended that you have a MyST account in order to save these workbooks. And I'll be using the login option today. So I just logged in with my MyST account. And now it's saying, okay, I'm logged in as me, my email, and I can click proceed to go to the available workbooks page. I will show here really briefly the last thing up here on this top bar. This top bar goes with you everywhere. This on the left, exposure time calculator, the user, and the help menu. If I click on exposure time calculator up here, it will take me back to the home page. So at any point when you're working in the ETC on the workbooks page in a workbook and you want to go back to the home page, you can always click the top here. All right, so I'll log in again, go back to the available workbooks page. All right, so there are a few things to see here. We have two sections, available workbooks and this sharing section down here, which I'll get to. But we have an ID column, a name. The version will be listed here if workbook was created in an older version of the ETC. If you try to open it, it will be read-only. And if you want to continue editing that workbook, you'll have to copy the workbook. And this allows you to compare previous results in the ETC. So that's why we have this. Each new release will make old workbooks read-only. There's a description if you want to add a description for your workbooks. And here I'll just create a new workbook, basically a blank new workbook to start with. You can see the ID number here, the name of the workbook. Load is how you enter the workbook, and then there are options over here to copy the workbook, as I mentioned before. You can rename it here to change the name and description, but you can also do that in the workbook itself. Move allows you to move it into a folder, and then remove is for deleting the workbook. So deleting the workbook means that you can no longer see it in your workbook list. It's still available, but it takes some work for the developers to bring that workbook back from the dead if you need that to happen. So be careful when deleting workbooks. I'll demonstrate really quickly if I create a new folder here. So you can give it a name and a description. I've highlighted this workbook already, and I can click Move, and I'll put that in New Folder. And now we can go in here, and you can see that the workbook is now in this folder. You can have any number of folders within each other in whatever directory tree that is most comfortable for you for organization. And this is a new feature that was just made available in ETC 2.0. So while we're in here, I've highlighted this workbook again. Now, once I've done that, down at the bottom it says User Access Permissions for New Workbook. I can enter an email address, only one at a time, unfortunately. We don't yet have the option to do comma-separated lists of email addresses. But I can click Add User by Email. This is for my deputy, Brian. So wait, it takes a little bit of time for the workbook to be shared for that to show up here. I'll just quickly go over the different permissions. There's read, write, grant, and revoke permissions. So read means that the person can read what's in the workbook. They can open it, but they can't make edits. Write allows them to make edits. Grant means they can share it with other people. So be careful giving this permission to someone, because then they can share the workbook and you won't necessarily know who it's being shared with. And then there's the revoke option. So this means that you can revoke someone's access to a workbook. And here, Brian has shown up as someone who can view this workbook now. And by default, only read options read permissions are given to someone the workbook's been shared with. And if I want to remove someone from the workbook, all I have to do is uncheck all the boxes, and that person no longer has access to the workbook. And that's because I have revoke permissions. One last quick thing on this page, I'll show how the context-sensitive help links work. So here is the blue question mark I mentioned. If I click on that, it'll take me to a relevant page. In this case, it's the overview page for the ETC. You scroll down a little, it shows information on how to organize workbooks, share workbooks, things like that. So that's all you have to do is click on those little icons. And one thing I did forget to mention are the other workbook options available to you. So I created a new workbook, but there are sample workbooks and example science program workbooks available. Sample workbooks include basic calculations for all the different modes and some of the specific observing methods. So solar system has a specific workbook, slitless spectroscopy, things like that. So they're pre-made calculations, so it's a good place to start, especially with coronography. If I need to do coronography calculations, I grab one of these. We also have example science program workbooks. These are associated with the example science programs in JDocs, and here's the page for that. So there are a number of these example science programs created prior to launch, but they walk you through the whole process of creating a proposal, from the idea to working in ETC to putting those values into APT, everything from start to finish. They have reference numbers here and titles for description of what's in it, and those are associated workbooks that are available in here as well. So that's a good place to see the start to finish process. So let's jump in and see how to use the ETC. So I have this empty workbook here. I will click the load button and it opens it up in a new tab. And there's a lot going on when you first look at it, but I'll try and walk through things as sequentially as possible. Just a quick note here at the top, we have the workbook ID. This matches the ID in the available workbooks page, and it's uneditable. You can change the name of the workbook or the description up here. And if you want to make notes to yourself, about why you made certain choices for the workbook or the calculations in the workbook, things like that. You can add them down here in the notes section, and those will be recorded for whenever you come back in the future and look and see, why did I do that? Well, you can leave some notes to yourself, a little time capsule down at the bottom. All right. So the notebook or the workbook opens to the calculations tab, but in most situations you'll want to first go to the scenes and sources. This is where you set up the source parameters to use in calculations. So there are a few different panes here. There's the scene pane, sources, the source editor, the scene sketch, which shows the sources within the scene, and then the spectrum plot for the source itself to show what the SED is. So I want to point out here that there is a default scene and a default source available in each of these new workbooks. You don't have to create these yourself. So these are ready to use. They have default values in them. The source has default parameters, but you can immediately start creating calculations and you won't get any errors in a new workbook. I'll highlight the scene here by clicking on it. It shows up in yellow. All of the sources that are in that scene will show up in green. And if I click on the source, in this case there's only one, if I click on that, you get this candy cane pattern of yellow and green showing that I've selected both of them. And now when I look in the scene sketch, here's a cartoon of what the scene looks like, right? We have a point source in the center of the scene. And the source spectrum here is just a flat continuum spectrum. Once I highlighted the source editor pane becomes available. So from left to right, we have the ID. This is where you can change the name of the scene. You can change the name of the source. You can even leave yourself a comment or a note here. There's a continuum tab. This is where you select the spectrum to use. So if you've uploaded a spectrum, which I'll show later, you can grab that from here in a drop down when there's something in there. Otherwise, the most common option is going to be a template spectrum. So we have many different options from analytic spectra to different stellar types, galaxy spectra, and then even the sun and the giant planets in our own solar system. Right now, the default is always a flat continuum in FNU units. There's also this option for no continuum. If you're just looking at an emission line, you don't care about the continuum, you can choose the no continuum option. That is something that can be selected. And then I won't be showing this during this webinar, but you can set a redshift and an extinction as well for your SEDs. All right, and then there's the renormalization tab. This is where you can alter the normalization of your SED. So right now, the normalization is 0.001 millijanskis, and you can see that by reading the plot. At 2 microns, obviously in this case, the position doesn't matter because it's a flat continuum, but you can change, if you have a spectrum with a different shape, you can change where you're normalizing to if you have that information. Alternatively, you can normalize within a bandpass. We have all the different JWST bandpasses available, HST, filters, and then a larger selection of other filters, ground-based filters. So we have, or in a lot of cases, like Johnson filters, Cousin filters, things like that. We also have Gaia, as well as Spitzer and Wise. So if you have information on your target for any of these filters, you can normalize it using that information. You'll want to select the Do Not Renormalize option if you have uploaded your own spectrum. Presumably, if you've done that, you already have it properly normalized and you don't want to apply an additional normalization. So you can choose that option to make sure that it retains its original normalization. Okay. I wanted to take a note here that I haven't changed anything, right? I've shown you the different options, but I haven't actually changed anything about the source. And that's because I want to show that if I make a calculation, I can jump right into this workbook and immediately make a calculation. So we go over here to calculations now. We have buttons for each of the instruments. I'm going to create a MIRI imaging calculation, and it will immediately return that. If I click on it, we see some more information about the calculation itself. But I made no changes in the workbook. All I did was open it and create a calculation, and I got a result out, right? It says it can be as simple as that. Unfortunately, the normalization and the SED that are available for the default are probably not very, can be very descriptive of what you're actually observing. Not going to be very relevant. So you'll want to change some of those values and then run the calculation. But it's very simple to do so for a point source. Let's go to that most basic use case, which is point source. Determining the SNR of a point source, which is what many other ETCs do, similar to the HST ETC. It's using only point sources. You're setting the parameters for the point source, and you're running the calculation. So let's see how to do that. We'll go back to the Scenes and Sources tab now. We still have this selected. So let's start with the Continuum tab here. So this is where we select the source SED. Right now it's a flat continuum. Let's change it to something more exciting. So let's go to a galaxy spectrum. So we'll select Galaxy Spectra from Brown et al. 2014. And in the drop down below here, there are a lot of different options for different kinds of galaxies. Let's stick with the top one here, NGC 3521 as the template, and we'll click Save. So this updates the source, and you can see that the spectrum is now a galaxy spectrum rather than a flat continuum. But it's still normalized to 0.001 millijanskis at 2 microns. So let's change that normalization. Let's assume our galaxy isn't that faint. So go to the renormalization tab. We'll select normalize in bandpass. And then we have different options here for the units. Let's choose Vegamag. Let's set it to 19. And let's say that we have this information. I don't know if this would be an accurate use case or not, but let's say we just have it in Gaia G filter. And we can click Save again. And so note here, let's keep in mind this is 0.003 at the top. Let's click Save, see how that changes. And now we're a few orders of magnitude brighter with this normalization. So, all right. So I made changes to the calculation. I made changes to the source. And if I go to calculations now, you'll see that the calculation automatically reran when I changed something changed some property of the source. And the SNR is now much higher, 360, an SNR of 360 now, instead of before it was in the tens. We automatically have these rerun so that there's no confusion about what changes were made and what the calculation results are. So be careful if you have a calculation that takes a long time to run. Try to make as many of those changes as possible all at once, then click Save, and then the calculation will restart. There are some modes that can take a little longer, a minute or two to run. So just something to keep in mind there. And with that, we have successfully run a calculation of a point source that's different from the default source. And this is going to be the majority of most of the calculations that you'll perform in the ETC. So you now have the tools you need to run your calculation for the majority of sources. And this is, there's a lot going on in the ETC, but I changed two different things. created a calculation, and got a result that I can use for writing my proposal now. Now that we've done a basic calculation, let's examine some of the additional information and other things we can change on the calculations tab here. So what we see here on the left, this is the calculation list pane. You have information about the calculations, the ID number. The checkbox here has a specific color around it. So if you have multiple calculations, you can plot and see different colors down here in your plot. And have the correspondence between the color and the calculation. The name of the mode that you're using, this is not editable. So for mirror imaging, it'll just say mirror imaging. You can't change the name of this. The central wavelength, this is based on the filter that was selected. Which scene is being used? We're using scene 1. The total time listed here, and the SNR. The last column here is saying, it'll give you either a green check mark saying the calculation completed successfully, and there's no saturation, or it'll be a yellow exclamation point inside a triangle, meaning that there's saturation or some other issue with the calculation. And on some occasions, you'll have a red X, and that means the calculation didn't run at all. And that's likely due to a mismatch in wavelength regions or something like that. Over here, we have the calculation editor pane and multiple tabs here. I'll come back to that later. I want to show the images and plots first. So we have the images here. We have 2D SNR image, and you can hover over this to get the position within the image as well as the SNR. And you can zoom in. You can take snapshots, things like that. There's the detector. So this is nominally what the image would look like on the detector. And for lower SNR calculations, you'll see a bunch of noise out here. There's also saturation. We don't have saturation anywhere, so this value is 0. It'll report 1 for partial saturation and 2 for full saturation. I'll discuss that later. And then groups before saturation. This is giving you the maximum number of groups you can specify prior to saturation occurring in a particular pixel. And I'll discuss that later as well. The plots, it's a little uninteresting right now because we have an imaging calculation, but for spectroscopy, it'll show the full spectrum in here. But you can hover over on this as well. So this is showing the central wavelength and the SNR. You can also change the scaling down here. And then the reports tab. So this provides some information on the calculation that was run, if there are any warnings or errors, and then downloads. You can download the data products for this particular calculation and work on them offline. Okay, so the meat of this is the calculation editor pane here. We have 5 different tabs. It opens to the instrument setup tab, but let's walk from left to right again. The scene tab, you'll notice looks a little familiar. That's because it's exactly the same thing that you see when you go to scenes and sources. This is just a convenience that's provided so that you don't have to switch over to scenes and sources, make changes, switch back to calculations. You can just click on the scene tab here, make the changes you want to your source, and go from there. We also have added the little CS context sensitive help link here that you can use to go to a relevant JDocs page, which is the same one that's used on the scenes and sources tab. You can also use this to change which scene you're using in the calculation. Right now we only have 1 scene. You can have multiple scenes and you can select from them in here. The backgrounds tab. So you can select different backgrounds for your calculation, depending on the position on the sky your target is at. And then you can choose either a dated background, so a particular date, if you know exactly when this calculation has to happen. You can choose the position, choose the time, and it'll give you the most accurate possible background for your calculation. If you don't know when that's going to happen, you can choose one of these options instead. For background configuration, there's an option for no background. Not recommended for realistic calculations, obviously, but it is available. And then there's options for low, medium, and high. And these correspond to the low corresponds to the 10%, 10th percentile background for the visibility of your target over the course of a year. Medium is 50th percentile and high is 90th percentile. So if you want to get a conservative estimate of your SNR for a particular source, you can choose the high background option to get the lowest SNR in that situation, just as make sure that you're getting as much time as you need in the worst possible scenario. The instrument setup tab. This is where you select the optical elements for the particular mode you're working with. So for mirror imaging, there's only one option, and that's the filter. It's very simple. There are more complex modes that have 3 and up to 4 different options here to select. But for mirror imaging, it's simply a drop-down menu with all of the mirror filter options. And right now we have F560 selected, which is the shortest wavelength filter. And then there's a system throughput plot. So this shows the throughput from mirror the optical elements in the instruments and the detector QE, all that stuff wrapped up and showing the total throughput for this particular filter. All right, and this is where the magic happens. Detector setup. This is what I was discussing earlier with my my PowerPoint art with the frames, groups, integrations, and dithers. So this is where you specify all the detector parameters here. You have options for different subarrays. So the default here is full, but there are other options for smaller subarrays. In most situations, you want to use the full subarray unless your target is very bright, in which case you want to choose a smaller subarray instead to decrease the frame time. So for instance, we look down here and we see total exposure time for this setup. Right, we have 277.5 seconds. If we choose a smaller subarray, that'll automatically update to a much lower value because the time it takes to read that subarray is much lower. Now if I switch back to full, when we see readout patterns, for Miri, there are 2 options, fast and slow. Fast is recommended. This is basically a rapid readout pattern. Every frame is a group. You can also select the groups per integration. This is the number for Miri. In this case, is the number of non-destructive reads up the ramp. The default is 100, but we can choose a smaller value. I'll demonstrate that later. And then integrations per exposure, and then total dithers. It's worth noting that the ETC is not actually performing a dither with these calculations. You're not actually moving the source on the detector. This is just a mathematical noise savings. So you'll decrease the noise as the square root of the number of dithers. It's useful for connecting to APT if you have a certain dither pattern selected there, but you're not going to see multiple images of your source in the images down here. All right. The best way to optimize your calculation, so to get the highest signal to noise in a given amount of time, you want to maximize the number of groups per integration before hitting saturation. So for very bright sources, you're kind of constrained to small numbers of groups to begin with, in which case you want to increase your integrations. But for fainter sources, you want to go as long as you possibly can before you hit saturation or before you hit a recommended limit for total time, which is based on the expected number of cosmic rays. That's usually 1,000 seconds or so. But this will give you the highest signal to noise for a given time. Increasing integrations is kind of like taking multiple images with a CCD. Where you get the square root of n increase in SNR. it'll increase much faster for groups. I'm going to demonstrate this using the batch expansion options. So let's change this first to groups per integration of 10 and hit calculate again. You notice the SNR decreased, but for this example, I want to start with 10 groups. Now, I can start exploring the parameter space using a batch expansion. So there's a drop-down menu up here where I can expand over groups, expand over integrations, or expand over filters. So in this situation, if I clicked expand over filters, I would get calculations for all of the other MIRI filters. I'll choose expand over groups as the first option here. So I choose a start value for groups, started at 20, step size of 10, and 10 iterations. So this will create 10 new calculations, each one of them having 10 additional groups starting at 20. So if I hit submit here, you'll see all these calculations immediately created. And the blue line there means that the calculation is currently running, and that moves so you know that it's not frozen. Okay, so if you don't like small numbers in the bottom, you can change the ordering up here. So I'll put that at the top. Let's do the same thing, except for expanding over integrations. So we'll have a start value of 1, step size of 1, and again, we'll create 10 new calculations. So we'll get 10 new calculations where the number of integrations is increasing by 1 each time. And we'll click submit. And it's creating all these calculations down here. And now we can view all these calculations at the same time. To do that, I'm going to click this little checkbox icon up here, select all, and then if I go down to the plots, you can see all of them. You have different signal noise ratios, but they're all using the same filter. So this isn't a particularly illuminating plot. So instead, I want to look at the signal noise as a function of time. And if I do that, I see 2 different curves here. And what we're seeing is the bottom curve. These are the calculations where you're increasing the number of integrations. And this is the top curve is increasing the number of groups. And you'll see that each one of these dot pairs, right, they're lined up and give the same amount of time, but you have different SNRs. So for 300 seconds of integration time, you're getting an SNR of 262 for increasing integrations. But for that same amount of time, you're getting an SNR of 353 by increasing number of groups. So this is just to demonstrate that you really want to increase the number of groups first before integrations, and that's how you get the best results. So we have all these calculations now. There are about 21 of them. I'll note that you can only have a maximum of 50 calculations in a workbook at any given time. And that's just to make it possible to load the workbook in a timely manner. If you have thousands of calculations, it'll take forever to load it. So we limit that to 50. But right now, I don't want these calculations anymore. I can quickly delete all of them because I have all those checkboxes marked. I can click delete marked calculations, and this will do a batch delete. And it'll ask me, do you want to delete all of these things? And I will say, okay. And then it will deletes all of them. I don't have to click each one individually. All right, so now we've walked through basic calculations with point sources. I've shown the best way to optimize the calculations. Now let's do some quick troubleshooting. You're gonna encounter some issues along the way, either based on the source that you're using or something else. So let's see how to handle some of those. I'm going to create a MIRI imaging calculation again. And I'm going to click on this and go to instrument setup. And I'm going to change the filter to the longest wavelength. First let's take a look. You can see the PSF here. If I change to the F2550W, which is the longest wavelength filter, and then click calculate, we end up with a much larger PSF, because it's longer wavelength, a lower signal noise ratio. It's a generally lower throughput for this filter. And you'll notice now that we have a warning. So this is what the warning symbol looks like. And it says something went wrong in the calculation, right? There's something that's off. And now the warnings tab down here in the reports is red. So it's saying, look at me, there's something that happened here. So because this is the longest wavelength, you're getting a lot of self-emission from the telescope, and the background is saturating in this filter. So it says, consider making the observation shorter. Okay, so how do we make the observation shorter? And I guess first I should mention, this says partial saturation. That's the warning here as well. There are 3025 pixels saturated at the end of the ramp. Partial saturation means that you've hit saturation somewhere up the ramp, and you can remove later on. You can remove the saturated groups and still get usable information. But it's obviously not an ideal way of doing an observation, because you're using telescope time that you're ultimately not able to use for your target. So you want to try and avoid partial saturation. The scarier one is full saturation. That didn't happen in this case. Full saturation is only for very bright sources, and that means that you hit saturation within the first group, and there's nothing you can do to get that information back. You've hit saturation, nothing is usable. So in that case, you want to change your readout pattern. You want to change the subarray. Or if it's still, that doesn't work, then your target is just too bright to observe. Maybe you want to use a spectroscopy mode, higher resolution mode, something like that, rather than imaging. But in this situation, we've hit partial saturation, and that's because of the background. If we look at the groups before saturation plot here, because it's the background, we're seeing that we've hit saturation all the way across. And the easiest way to fix this is to look at the results. And if I go down to here, maximum number of groups before saturation. This is the minimum value of the groups before saturation plot. And it tells you this is how many groups you can specify before you hit saturation. So the default is 100 groups for mirror imaging. If I change this to 14, as it says for that quantity, and hit calculate, it will show me that, give me a green check mark again, right? The calculation is no longer saturating. If, for instance, I change this to 15 instead, I'm getting the warning again. So 14 is the maximum, and this is where we want to be. This is basically the maximum SNR we can get before we hit saturation with this particular filter. We end up with a signal noise of about 13. Okay. I'd also like to point out another change you can make here. So keep in mind this is 13.33 for the SNR. We haven't looked at the strategy tab yet, so let's go to the strategy tab up here. And this is the imaging aperture photometry extraction strategy. So this is how you get how you calculate the SNR for your calculation. You can specify where you want your aperture centered in the scene. You can choose which source to center it on if you have multiple sources within the scene. But we're going to focus here on the aperture radius and the sky annulus. So if we look here, the aperture radius is 0.3 arc seconds. And if we try and show both those at the same time, if we look in this image, we can hover over and get positional information in the image. If I go out to an X of about 0.3, which is here, we're seeing that the aperture is not containing all the flux of the PSF. And in fact, the inner sky annulus, which is about here, is containing significant flux from the source. These aperture and sky annulus values are defaults for this mode. And we should probably change them so that we're not subtracting some of the source from itself. Right? Let's see what the signal noise really is. So let's change this to 0.6 arcsecond radius. Then we obviously need to increase the sky annulus as well. So we can change this to 0.8 and 1.2 because those values still fit within the size of the scene. And now if I click calculate, all right, we're starting at 13.33. If I could hit calculate here, we're now up to 22.4, right? We're no longer subtracting the source from itself. We're getting a higher SNR, right? This is generally what you would do if you're analyzing the data yourself. You're not going to use defaults for that, right? You're going to use what makes the most sense to do. So we can change those values here to get a more realistic SNR. All right. So we've walked through imaging. I want to show a spectroscopy mode. It's going to take a little bit of time for this to run. So I'm going to do a near spec IFU calculation. I'll kick that off. So moving on, the calculation has returned nice and quick, quicker than sometimes it usually is. And I can click over to this calculation instead. Let's go back to here. And looking at this, right, we see a different PSF. And let's change back to signal noise as a function of wavelength. And there you can see the spectrum for the target. And you can hover over this to get signal noise every 100th of a micron here. I'll continue showing a little bit of troubleshooting. When you create a near spec IFU calculation, the default is the G140M filter. Let's say we want to change to the G235M. Right, we get all this red text all of a sudden, and we can no longer run the calculation. So what's going on here? On the strategy tab for this mode, we have an additional option here called the wavelength of slice. So while the calculation is running over the entire spectrum in the wavelength range, and you're getting information along the way at various wavelengths, the value reported here in the calculation list and the value in the reports tab, the values down here, correspond to this particular wavelength. Obviously, you can't show all of this information as text all at once, so you have to choose a particular value. And by changing between gradings, the wavelength range is changed, and the strategy tab does not automatically update. In general, the ETC avoids making changes for the user that the user doesn't see. And so we have the old default wavelength of slice for the shorter grading. So we need to fix that. So you can either do that by typing in a value directly into this box, and helpfully the wavelength range is provided up here, so you can choose a value within that. Or we can use what we call the fix it for me button, which is this here. It says update to midpoint, 2.4 microns. If I click that, the warnings go away. The wavelength of slice has been updated, and I can now recalculate. And I'll show quickly here for the IFU mode. There are, as with the mirror imaging calculation, there's one option, right? It's just aperture photometry. But for the IFU, there are actually 3 different strategy options. The default is IFU aperture photometry. So it's basically imaging photometry at every slice in the cube, right? So you're specifying your aperture, your background annulus, and you're doing that for each wavelength in the cube. The other option here, the next one is IFU on target 2-point nod. This is basically when you change it, it does this, asks for the change in wavelength of slice. But for this particular option, the 2-point nod, you're basically, you're moving the source a little bit, and you're doing an A/B subtraction, so you end up with a positive and a negative PSF in your images, and you can select how far you want that nod to be, things like that. And then the third option is IFU on target and off target pointing. This is a dedicated background observation, right? You're observing your target, and then you're going over here and observing a background. And the ETC mimics a flat background that then gets subtracted from the science scene. In this case, you only specify an extraction aperture radius. All right. Let's just move back to this to get rid of the. Yeah, that's a little bit annoying when it does that because it resets the default each time you change the strategy. So you have to use the Fix It For Me button to change that. All right. So I've shown a lot of changes and things. I haven't clicked Calculate to recalculate the calculation. If I click to a different calculation, it will ask me, say there's unsaved changes, right? It's not automatically rerunning the calculation for me. Do I want to continue and lose those changes, or do I want to recalculate first? So I'll show what happens if you hit continue, right? So now I've switched over to imaging. If I go back to this one, you'll see that we're back to the 140M. It erased all the changes that we made along the way. So if you want to retain those changes, make sure to hit calculate after you've made them. Otherwise, it won't save that information. So now let's look at how to create more scenes and sources. So go back to this tab, Scenes and Sources, and we can create a new scene by clicking the New button here. We get Scene 2, and we can create a new source by clicking New here as well. And if I click on Scene 2, right, we're not seeing anything green over here. There's no sources listed here. Let's add source 2 into scene 2. We can do that by highlighting both of them and clicking add source. Similarly, you can remove the source if you don't want it in there anymore, but we want to add it in for now. Excuse me. And if you want to use this as the default scene when running calculations, you can click the little purple star here. So you can see purple star equals default scene up here. So now that I've selected this, any new calculations will automatically use scene 2 instead of scene 1. And for this particular source, let's do, let's not use a template spectrum this time. Let's use an uploaded file. Right? Currently, there's nothing that's been uploaded, so we have no options here. We can go to the Upload Spectra tab, the next one along here, and select a file from our computer. So I will go and do that. So I'll choose a file. I'm going to choose this Pluto file. I left that in the Slack yesterday. And I'm going to click Open. So if you want to play along, you can grab that. It shows up here, and now I need to click Upload to upload it to the ETC. And then I should get a little pop-up, and it's saying successfully uploaded, and it's detected these wavelength and flux units. For text files, it's not actually detecting the units. It's just assuming that your wavelength is in microns and your flux units are in millijanskis. If I click OK, then I get a success here, and the spectrum shows up here. It has the name of the file, the minimum and the maximum wavelengths. You can also upload FITS files, and we can show that here. There's a context-sensitive help link. There's information here. You can upload FITS files. You can upload data file, .dat or .text files. And as I said, if you're uploading an ASCII file, it requires specific. You have 2 columns with specific units in them. Otherwise, you'll get weird answers because it's actually, it's assuming if you don't have those units, it's assuming that those are the units. It's going to make a mess, right? It's worth noting that you cannot delete spectra. You can overwrite them though. If I had made a change to this file and uploaded it with the same name, it would overwrite this one. So you can't delete, you can't download files from your workbooks. But when you share your workbook with someone, the file does come with it. So that does work. There are also a lot of troubleshooting things that can happen here. I've chosen a file that is well behaved, but if you have a file that has duplicate wavelength entries, has wavelength entries not in the right order, or if the file is too large, if it's over 10 megabytes, then you'll get an error, and it will not upload the spectrum into the ETC. And the page that I showed before has some troubleshooting information, right? It shows the information you need to have, and you can use PySynfo to check if your file is valid to be uploaded. Okay, so now I've uploaded the file, and now let's go back to Suite Scenes and Sources. We still have Source 2 highlighted, and now we see in this dropdown that our uploaded file is available. So we can click this, uploaded file as the option, and then go to the Renorm tab. We already have it properly normalized, so let's click Do Not Renormalize here. And now I'm going to click Save. You can see that the spectrum is updated, right? It started off as that flat continuum source, and now we have the reflected component at short wavelengths, and then the uptick in thermal emission from Pluto over here. So this is just a thermal model that I have on hand. All right. So now we have this created, and let's go back over here, and let's just create a quick near-cam imaging calculation. So go complete quickly. And if we click on this and click on scene, we see that it's automatically using scene 2, right? Default scene is scene 2. It automatically used the Pluto scene. And because it's a short wavelength calculation, it actually saturated pretty badly for this particular source. So so we just showed how to create new sources and upload a spectrum. Let's start fresh with a new scene and a new source. And I'm going to do the same. Oops. Yeah, so I made changes, but I'm not going to save that. Let's just continue. Do the same trick again, highlighting, add source. So now I have source 4 in scene 3. And I'm not going to change the continuum, leave it as a flat continuum. Not going to change the renormalization this time because I want to mimic a source with a low continuum, but an emission feature. So let's add an emission feature to this flat continuum. So I've gone over to the Lines tab here. We have a few different options we have to input, right? So there's line name, let's call it 02. Line center, put it at 0.73 microns, a line width of 4,000. These are just values I'm putting in from that I have on hand here. But, whatever values you have for your line, you put them in here, right? So line center, the line width in kilometers per second, and the line strength in flux density or in flux units. We have all these in here, but we haven't created the line yet, right? We have to click this green add button, and now this line shows up. If I want to make changes to the line, I first have to click on it, and then I can say, okay, let's change this, and then hit update. So I've updated the line width, and if I actually wanted to go back, I can update it again. So I've created a line now, and if I click the save button, that will show up. You see it's a very short wavelength line here, but it's showing up here, the strength over here. I'm going to make this scene the default scene. And then I'm going to run a new calculation, a fixed slit calculation. So that'll take a shorter time to run. So it's I don't care. Okay, near spec fixed slit. And the grading is the prism clear. So this goes from 0.6 to 5.3 microns in one shot. And you can see down here in the spectrum where we have the dashed line, and it's showing the emission feature and the flat continuum. But because of the throughput, you actually get a not flat continuum in this situation. But now, when looking at this plot, if I look at the peak here, it's saying that the signal to noise is 91, but the signal to noise reported here is less than 4. So what's happening here is that the default wavelength of interest, or which is same as wavelength of slice, is somewhere out here, right? 2.95. If we want to get some information on the feature itself, we need to change this to the position of the feature. Click calculate again. That'll update the values reported, and now we get the value of 91. It's worth noting that the ETC reports signal to noises as on a per pixel basis. This is not an integrated SNR over the line. The ETC does not have a capability right now to do integrated line SNRs. If you want to calculate that, you have to download the files, and we do have a knowledge base article that walks through how to calculate the integrated emission SNR. And I think, if Brian hasn't already done so, maybe you could post the link to that in the Slack. So we do have a prescription for walking through how to do that using the specific data products available in the downloads. So far we've worked with basic source manipulation, right? Changing the SCD, changing the normalization. We've worked with uploaded spectra. We've added some lines. We've even shown how to put multiple sources within a scene. So now let's go to one of the last things you can do, one of the last basic things you can do with sources. So I'll do another create source and scene, add them in, and then I'm going to leave the continuum and renormalization the same, and I'm going to go to the shape tab. So by default, sources are point sources, but let's choose extended source, and we get more options when we do that. So we see here that we can choose different flux distributions. We have a flat distribution, right? And when I change that, it changes what things look like in the scene sketch. We have a 2D Gaussian, which is the default. There's two different versions of Sursic. This is mostly for creating galaxy spectra. And then a power law spectrum, which is primarily used for comets. So you have a flat core, and it drops off with a power law beyond that. And you get different parameters over here depending on which option you select, right? So let's go with the 2D Gaussian option in this case. And we see the parameters over here for the X and Y directions. Let's make a source that is 0.3 arcseconds in X and 0.1 arcsecond in Y. And you see how that continues to change as I alter things over there. There are two different options here for normalization. You can choose an integrated flux. So if I look on the renorm tab, right, it's saying you have this much this much flux. It's a flat spectrum, so you have this much flux spread across the entire extended source. Whereas if I choose surface brightness, you have options for per square arcsecond or steradian, and then where you're normalizing it. And then if I look at the renorm tab now, the units have changed over here, right? So this didn't exist before. It now says per square arcsecond. So this gives you the surface brightness units in your renormalization options. If you choose, you can choose to upload a spectrum that is in surface brightness units. But in that case, you want to make sure that you select the proper extended source with the surface brightness normalization choice. So that is something that you can do. I'm just going to work with the integrated flux right now for the rest of this example. So those are the options for creating the shape. And now I can also offset it, or go to the rotate it rather. So I showed earlier how to offset a source within the scene. If we only have one source, there's no point in applying an offset, but we can change the orientation. So I'll change that to 45 degrees, and we get something, looks more or less like a galaxy on the sky, I suppose. Rather than, the orientation doesn't necessarily matter, but it is something you can change. So I've created this source, rotated it, and now I probably want to make this the default scene first, and then I'll go and create a near cam shortwave imaging calculation. If I click on this, right, I see the source within the scene, or in the image here. Here's what it looks like on the detector, right? A little noisier than some of the other calculations we've seen. You'll note again, for near cam, the default aperture radius is 1/10 of an arcsecond. If we look at that on here, that's fully within the target here. And then the sky annulus is also subtracting a lot of flux from the source itself. So again, let's alter this. Let's change this to get more reasonable results. Change that to 0.4, right? That takes us beyond the edge of the primary edge of the source. Change this to 0.6 to 0.9, and that keeps it within the scene. And we'll click calculate. And we were starting at a 19.6, an SNR of 19.6, and now we've almost doubled it to 36 by making sure that the aperture covers most of the flux, and the sky annulus covers, avoids as much of the source flux as possible. Something for future ETC that we've been thinking about and working on is adding drawings that show the aperture and the sky annulus in the images. We're excited for that for whenever it makes it into the ETC, but it'll help to visualize better the values that you're putting in here. But at this point in time, we don't have that capability, unfortunately. All right. One last thing here. So I'm going to go back to the Available Workbooks tab, and I want to show, while we're talking about extended sources, I want to show the extended source template sample workbook. So I've created this, and I'm going to load it. There are no calculations in this workbook, right? It's the only template one that we provide that doesn't have any calculations, but it has a lot of scenes and sources, right? So there's a lot going on here. It provides templates for star clusters, right? So we have a few different options, random positioning of stars. The normalizations haven't been changed on them at all, but they're just oriented to more or less have some stars that are overlapping, others that are farther away. Circular ring, so this is ring viewed face on, and then an elliptical ring, so viewing at some angle. And this makes use of multiple sources. All the sources in the ETC are elliptical. So this is kind of a little bit of a kludge to try and get another shape out of ellipses. I've also provided an arc. So this is just a portion of the circular ring, and then a comet, which makes use of that power law flux distribution for extended sources. So yeah, if you want to use one of these shapes, all you do is load this workbook, select which one you want as the default, and then create a calculation using that. You'll probably likely want to update the normalizations on the various sources in it. All right, so you see when I highlight this in yellow, all of these show up in green. There are 16 different segments within this ring, so you'd have to update the normalization in each one, unfortunately. But it places them in the right spot to start with, which is, I created this workbook, and yes, it took a little bit of time to get these things in the right place. So certainly make use of that and update the normalizations as you need to.